So remember that velocity is equal to the change in distance divided by the change in time. And while we could look at the total displacement divided by the total time, that only gives us the average velocity, and it's continually updating. So we've got a new average, a new average, a new average, a new average velocity. But what I'd like to do, instead of the way this video does it, is instead look only at the velocity during each time segment, which is 1/10 of a second long. So what we're going to do is instead we're going to take this delta D right here, which is in centimeters, and we're going to divide it by 1/10 of a second. So 0.1, 0.1, 0.1, and so on. So when we do that, 0.8 divided by 0.1, we just move the decimal point one place to the right. Okay? So this 1.3, we just move it one place to the right, one place to the right, one place to the right, one place to the right. And so our times here, or pardon me, our velocity from 8.0, 1.3, pardon me, 13.0, 18.0, 22.0, 26.0, and so on. So it's easier. So you just move the decimal point one place to the right in this column. Okay? Because otherwise you're taking this number, 8.7 divided by 0.5 or 11.8 divided by 0.6. Okay? That running average of the velocity is a valid way to look at this data, but it's not the way I want to look at it for this part of the lab. Does everybody understand how to do this part right here? All right, so it's a lot easier. Now your time is still going to be the same. It's still going to be 0.1, 0.2, 0.3, 0.4. It's the same as time over there. But all we're doing is moving the decimal point over one to get our velocities. All right, now I'm going to show you the video about how to set the graph. To do this graph, remember we're going to have our data over here and our graphs over here with these little flips to look under. What you write underneath should have been with the video yesterday for the first one, and it'll be right after this page today, in case I don't remember to say it later. But if you just click next at the bottom of the screen, it'll take you to this before it takes you to the submittal, where you're going to take a picture of both pages at once, a single picture. You should also have your graphs color-coded, so there's two different ones. So on my book, this is green and this is purple, so I also have a green and purple line and a green and purple line here. Okay? It doesn't matter what colors you pick, just so long as this color, and you can shade the top or circle the top to make sure that it matches the colors of your graph. So let's watch the video up to the point where we're going to do something different, and it's just a few minutes, and at that point, up until then, all it's showing you is how to do your lines. In case you forget, I've got some of the comments about how it's changing in red above the video here. So if you just look above the video, you should be able to see some of the changes there. So this video starts off showing you how to scale your graph, and there's no changes there. You should be scaling your graph the way it says in the video. But when it comes to drawing our line, there will be differences. So I'll tell you those when we get there.
And I'll show you why. Now we want to make sure that our axes line up pretty closely on the graph, so that when you compare them, you are looking at it pretty close. So all I'm going to do here is just kind of make sure that my new graph has my x-axis in roughly the same position. So starting from this edge, and that one's 0, and then I'm going to count, same as we did before, whatever your highest time code is. Mine is 1.3, so that's going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.9, 1.0, and 1.3. So you can see that on my displacement graph and my new graph that I'm using, that they're going to be in the same position. remember the wires as well. And label your access time in seconds. Time in seconds. Time in seconds. Always put a label on your axis. Always put
Now, she
units.
did all that to show you that the time axis is the same on both graphs. That should be identical on both graphs.
So now we're going to, again, take a straight edge, and right along here, you're going to draw in your y-axis. All the way up. This one is going to be velocity in centimeters per second, so go ahead and label that. Velocity, centimeters per second. Now we're going to scale it. So remember, how to scale. Look at your velocities. Find the highest velocity.
So which is the highest velocity, either the top set of numbers or the bottom set of numbers? Find the highest velocity and circle it. That's going to be what you're using as your basis to scale your graph.
Then you're going to count how many lines you have available on your y-axis.
You probably have more lines available because your graph paper is smaller boxes.
5, 6, 7, 8, 9, 10, 11. I only have 11 on this graph. So I'm going to take my calculator, and I'm going to do 80. That's my highest value, divided by 11 lines on my graph. 7.2727277. So remember, we always round up when you're scaling the graph, so I'm going to round this up to 8. And on my y-axis here, I'm going to count by 8. So 8, 16, 24, 48, 56, 4, 72, 80. Now you're going to plot your data. Remember to use, again, the same two colors that you used before. Mark it somehow. Again, I've got mine written in a color, but you can also shade in your headers. So I'm going to do red for the first one. And I'm going to do purple for the second one. You can do whatever colors you like, as long as it's two different colors, so you know which line on your graph goes with which data set. So now I'm just going to plot my data points. And I know that you can't see all of the blue lines on my graph paper, but that's okay. You'll still be able to tell what it is that I'm doing. So again, you're looking at time and velocity. Okay? Time, velocity, time, velocity. Make sure you're only graphing time and velocity. Alright, once you have your
All right, this is where we differ on what we're going to do. Let me get to a point where she's got that shown there, and I'm going to pause it. Okay. So on the original video, because we did our velocities as an average, as a running average, then it was appropriate to start at 0 and go to this last data point, which is indeed how she told you to draw the line. Draw it from the last data point to the axis. All right? But we're not doing that. We're looking at the individual velocities for each separate tenth of a second, unaffected by whether they're being rolled into this ongoing average or not. And the result of that is that some of the data, your data may not line up
exactly the same way. So I'm going to add some extra data here to try and show you something. Let's pretend that these data points that I added on here are the same data here, and we get an average line that looks like this. Wow, that's not very straight, is it? Let's pretend also that I can draw a straight line. Notice that the straight line does not go into the origin. And there is this little y-intercept right here. I call it a y-intercept because that's what you're used to. But it's not a y-intercept at all. What is this axis? Velocity. So this is a velocity intercept. All right, this is a velocity intercept. Now, let's take a look at how we collected our data to explain why we might have an intercept. If this is the paper tape that we looked at, and we made lines where we had the dots, the double dots, and we measured the distance between the lines, we had that big fuzzy looking blotch at the beginning where the thing was sparking over and over again on the paper before we let go of the bus, right? And I told you to ignore the space between that blotch and the first set of dots. Some of you, it was so unclear that you even ignored it till the second set of dots to begin your measurements, and that's okay. All right? But the reason we have to do this is because we don't know if, first of all, we don't know where the set of dots is in that blotchy spot, but also we don't know if there's a full tenth of a second between those two because we let go of the bus at some random point between the sparks, right? So we don't know if that even is valid data. So I told you to skip that first bit. You could even skip a couple before you started recording your data. So what that means is that the bus, when we first started measuring its velocity, was already moving, wasn't it? It was already moving. So let's take a look at this line again from that angle. Okay? So I mentioned this as a y-intercept. A y-intercept is associated with a particular type of equation, the equation of a line, slope-intercept form. Who can tell me what slope-intercept form looks like when you write it down? What is that equation?
Like it starts from y.
Yeah, y equals mx plus b. Y equals mx plus b. But these aren't our variables. What is the y-axis again here? Velocity. So let's call that v equals. All right, m, that's the slope, but we know that acceleration is equal to the change in velocity over the change in time, and this is change in velocity over change in time. So m, the slope of this line, is actually a. The x-axis, what is the x-axis? Time. T plus, and then we have some other v, because we already agreed that this was some v-intercept, right? So we have some other v over here. Now, it can't be the same v. It's probably some other v. Okay? So we've gone from a math y equals mx plus b slope-intercept form to this. Now, I'd already mentioned that this is the initial velocity. If I rearrange this, I end up with v final equals v initial plus a t. That's the fourth equation on page 14. That's the fourth equation on page 14. Okay? So not only does the line that you draw, not only does it not go through the 0, 0, I don't expect it to, and our equation says that it probably shouldn't. Our first data point that we collect, by the time we collect that first data point, our bus is already moving, which means it has an initial velocity, which is what that intercept is. So when you're doing your graphing and it doesn't go through 0, 0, don't adjust your graph to force it to go through 0, 0. You do your best fit line
the best way that you can. If it happens to go through 0, 0, that's okay too. Okay, because there is some variance in what we consider to be best fit. Okay, if it had a negative y-intercept, we would know that's not theoretically possible. It wasn't going backwards when we took our first data point. Okay, but sometimes our data is of such low quality that we get results like that. Okay, but when you draw your best fit line, you try and draw down the center where you have about as many points above as below. You're doing a graphical average is what you're doing, a visual average of those lines. You do it with a straight edge, of course. You never draw it by hand. Okay, it should be done with a ruler. But don't be concerned about this. It's actually expected that there will be a y-intercept, because our theoretical understanding of the way this lab works says that bus must have been moving by the time we took our first data point, which means it should have an initial velocity that we just don't know. We could know it. Our graph will actually tell us that. It's not part of the lab. It's not required. But if I were to come back, later and say, hey, by the way, that bus, we calculated its acceleration, but how fast was it going when we first started collecting data? You could look back here and you could say, oh, it's going, looks like about 4 centimeters per second when that first data point hit. And you'd be right. Okay? So this data has an actual use for it. Now, she also, once this is done, I'm going to erase my ugly looking line and use hers. She goes on to talk about how to do the calculations here. And you should write this on your own graph. I'm not going to write it up there the way she does, because that's off on my poster board. So I'll write it right here. The slope is equal to the change in velocity divided by the change in time, which is equal to the acceleration. All right? And so what is that equal to? Well, we have to get rise over run. In the original video, it says, just grab that last point, right? And that's the rise and the run, and 0, 0 is the other point. Well, we're not going to do that, because that's not how we've decided to graph this. Instead, what we should do is we should look for a point where the line goes through a known point on the graph, and I found a couple of those that look really nice right here. These points are, on the graph paper, very easy to discern. They're very easy to spot. Now, when you're doing a graph, the points that are easy to spot of course, if it goes through a corner, okay, if you've got a line that goes through a corner like that, that's an easy spot, right? Because we can follow that line over there, and we can follow that line down there, and we know exactly where that is. But some other spots that are easy are like this. That spot, if that's right in the middle of these, right? Or something that looks like this. Well, let's see if I can draw that a little better. Something that looks like that. That's right in the middle there on that line. So in between, in the middle of the lines is a good spot to pick too. If it doesn't go through any corners, you can pick in the middle or something, depending on what your numbering system is. That works, right? So with this numbering system here, if I go over here, my rise, that's 56 centimeters per second minus, right here is 16 centimeters per second, divided by, so my run is down to here, and down to here, so that's 0.7 seconds minus 0.2 seconds. So that works out to 40 centimeters per second divided by 5 seconds. 0.5 seconds. There we go. All right. So now, 40 divided by 5 would be 8, but 40 divided by 0.5 is 80. So that's equal to 80 centimeters, that's a unit there, per second, and then per second, so that's per second squared. So my acceleration is 80 centimeters per second squared with this data here. Okay, so I did rise over run. I picked 2 points. I'm going to circle them. They are not points from my data table. They're points on the line. And that's an important distinction. When you pick 2 points from your data table, you're saying all the rest of those points don't matter. All the rest of those points don't matter. These are the 2 important points. And you don't know that, okay? The important points are the line, on the line, the slope of the line that you drew. After you draw that line, you should ignore all of the data points on that line. All of these other data points that are here, worthless. They're random noise. The thing that is the beautiful, perfect embodiment of your lab is that best fit line that you drew, which means your rise over run should come from that line, not those data points. Okay? So pick 2 spots on that line that you can easily identify and use them to calculate your rise over run. And like I said, going through a corner, that's easy to identify. Going through like a midway point, either here or here, those are also easy to identify. But use those to calculate your slope. After you've done it, make sure you circle it in the color of your line. And then if you have, say, another line, maybe you've got your other line over here with its associated points, then you do your other math over here. So you do your slope equals delta V over delta T, and then you got your rise numbers over your run numbers and your centimeters per second squared, and you circle that in your other color for your other line. Okay? Everybody understand what we're doing and how it differs from the video? You have to go back and watch the video. If you don't finish today, remember these changes.